Joshua Mundinger from Wisconsin, who will speak on twisting the infinitesimal set.
Thank you very much to the organizers for the invitation to speak. So, in this talk, K will be some algebraically closed field, and X will be some smooth algebraic variety. And the main motivating example is when X is G mod B, where G is some reductive root. And the main question that I want to answer, well, I won't answer it fully, but give some example, is how to quantize with divided powers. So all of the new content in this talk will be in characteristic P. But first I'll explain the construction that I'm going to generalize from characteristic 0. So in this first section, you can take K to be C. And what we're dealing with are twisted differential operators, so let me remind you how to define differential operators. So the ring of differential operators you can define inductively as follows. An operator on functions is a differential operator of order at most n if, whenever you form the commutator of your operator with a function, it's a differential operator of one lower order. So this condition is for all functions f. So this is some inductive definition of differential operators. And to get started in this induction, you have to say what are the operators of order 0. Those are just going to be multiplication by functions, so the O linear functions on those. So this is Poisson geometry, so I better talk about the associated graded of this filtered ring. It is functions on the cotangent bundle of X, and as was explained yesterday, whenever you have a filtered associative algebra such that the associated graded is commutative, there's a Poisson structure, and this isomorphism is an isomorphism of Poisson algebras. So, what is a ring of twisted differential operators? So, this is a sheaf on X. And I'll say TDO for short, twisted differential operators. So, a sheaf is a TDO if D is a filtered algebra associative, and we require the associated graded of D is, again, the associated graded of differential operators, which is, in this case, functions on the cotangent bundle. So these are, if you like, C-star equivariant quantizations of the cotangent bundle where I dilate the fibers. And in this case, there's a very nice classification of such quantizations. It's a lemma of Valenson and Bernstein. So here I really emphasize that X is over C, and they showed TDOs on X up to isomorphism, where the isomorphism has to preserve the filtration, etc., are in bijection with not just a set, but actually a vector space. And that vector space is the cohomology of a certain complex. So omega greater than or equal to 1 is the complex where I take the de Rham complex, but I replace functions with 0. And so, for example, if X was scalar, then what we're looking at is the first step of the Hodge filtration on the second de Rham cohomology. Questions? So, one of the interesting features of this description, as I said, is that the left-hand side is a Fourier set, the right-hand side actually is a vector space. So, for example, if I have some line bundle on X, then I can consider differential operators not just on L, but actually on any complex power of my line bundle. So for instance, I could take lambda to be 1/2, which appeared in Ivan Losev's talk yesterday. And this kind of construction is very important when you're dealing with quantizations in general. Okay, and so what this talk is about is when you try to do this story with this notion of differential operators in characteristic P. So I've run myself out of board a little bit, but from now on, we're going to take the characteristic of K to be some prime number P, and X will be as before, and now we treat differential operators according to this definition. This is the so-called ring of Grothendieck differential operators. Now, I suspect some of you have not thought about this ring before, so let me tell you one example. Let me take X just to be A1. So over C, we're used to differential operators on A1. It's just generated by the coordinate X and derivative with respect to the coordinate ddx. But in characteristic P, when you take these Grothendieck differential operators, again, you'll have coordinate function X, and you'll have ddx, but when you look at higher order operators, you'll have so-called divided powers of ddx. So 1 over n factorial times ddx to the n for all n greater than or equal to 1. Now, why does that make sense? Well, even though maybe n is bigger than p, so I can't divide by n factorial, I can still make sense of how this acts on monomials. This operator will act on x to the m by the binomial coefficient m choose n, x to the m minus n. If you write down the usual formula for taking the derivative n times and you divide by n factorial, that's what you get. So these rings are not finitely generated. And the old program of how to classify TDOs somehow used that these rings are generated in degree 1. This isomorphism is about that, and I'll say more at the end if there's time. So here's the main theorem. So X is a smooth algebraic variety. then, oh, I'm sorry, I did not tell you the main theorem yet. I better say the definition. So a Grothendieck TDO on X is, again, a sheaf of filtered rings D such that the associated graded of this ring is the same as the associated graded of the Grothendieck differential operators on X. So in this case, we saw differential operators on A1. The associated graded will involve divided powers of the cotangent coordinate, and that's true in general. This associated graded of differential operators on X is functions on the PD neighborhood of the zero section in the cotangent bundle of X. PD being divided powers. Okay, now we're ready for the main theorem.
Isomorphism is Poisson.
Yes, it is Poisson isomorphism, and in fact, it has to be given by a certain canonical map as isomorphism.
So there are subtleties in the definition of what a Lie algebra is in characteristics 2 and 3. Do those affect things in characteristic 2 and 3, or is this characteristic completely characteristic?
I think this works even in characteristic 2 and 3.
Actually, I meant 2. 3 is for graded.
3 is for superalgebras.
That's because
yes,
I'm
but,
interested in superalgebras.
The Poisson bracket on the cotangent bundle is a Lie algebra in whatever sense you want in characteristics.
In the correct sense. Okay.
But could you just say again, what does PD mean? PD neighborhood? Maybe I just missed it.
PD is French for divided powers.
Oh.
So, in general, you can imagine it looks like this when you try to globalize it.
Yeah, great.
So it's like formal power series where instead of just powers of momentum variables, you have like divided powers. Is it correct?
Yes, you have divided powers of momentum variables, but
There is no
polynomials,
power series.
not
just
zeros.
Just polynomials.
Okay. Are we ready for the main theorem? Or any more questions?
You can pass on it. I'm just curious. Is that, I mean, you put that in quotes, but is there kind of a space that makes that precise?
Yes, there is a space, but it is not an algebraic variety. It's just a scheme because
Right. I mean, I
the
guess you
ring's not
know the
finitely general.
functions, but like you're
yes,
saying
it is a.
Okay.
It is just spec of the functions.
Okay, great. Thanks.
Okay. So the main theorem, TDOs on X in the sense above, up to isomorphism, are in bijection, again with a cohomology group. It is so-called syntomic cohomology of X in weight 1. Sorry, is that too low? Yeah. Okay. So ZP1 means syntomic cohomology in weight 1, and in general, weight syntomic cohomology is something quite complicated to define and is of recent interest to people in arithmetic geometry. But in this case, there's a very concrete description. ZP of 1 is by definition, I take GM and I take p-adic completion in the derived category, so it's some kind of derived p-adic completion, and I have a shift.
So it doesn't depend on K.
So the objects on the left-hand side are k-linear objects. But yes, the right-hand side.
Does this have a differential form description of any kind?
Yes, this does have a description in terms of differential forms. So this is due to Illuzi. So there's a map from here into some Duran-Witt complex. So now instead of x, you can think maybe x is over k, but now I'm looking at some lift of x over the p-adic numbers. And again, I have to take forms of degree greater than or equal to 1. And it's actually not, so it maps into here, and the image is exactly the subspace where the crystalline Frobenius acts by weight p. And it turns out that this is an isomorphism. This is using that k is algebraically closed. And the map here is d log. This ZP of 1 was defined in terms of GM, so some units. And when I have invertible functions, I can take d log of them, and I'll get some differential forms. And what Illuzi described is some p-adic version.
But if you have something like flag variety, this will be just ordinary cohomology with coefficients in the p-adic.
Well, so let me give another description of this, which will say what it is in the case of the flag variety. There will be some p-adic things, yes. So here's another description of this group. There is a short exact sequence. So this H2 of x coefficients in weight 1 syntomic homology maps to the Tate module of the Brouwer group. And then the kernel is the Picard group of x tensored with ZP. So I should say what the Tate module is. This Tate module is, I start with a Brouwer class of order p, I map onto it from Brouwer classes of order p squared by multiplication by p, and I can make this tower, and I take the limit, that's the Tate module. So it's a collection of p power Brouwer, an element here is a collection of p power order Brouwer classes. And over here I just have usual line bundles, but I can tensor with z.
Can I ask a question? I don't know, maybe I should save it to the end or?
Go ahead.
Okay, so if I remember that differential operators in say characteristic P have a big center and look like a matrix algebra over the center.
These are divided powers.
Yes, so, so thank you for this
I guess I just wanted to ask if this appearance of the Brouwer group is related to.
yes, so the appearance of the Brouwer group is related to this phenomenon of that differential operators relate to matrix algebras. Now there are two kinds of differential operators in characteristic P, as was said. This is the kind where you don't have a big center, but still what you have is that the differential operators on X are a union of matrix algebras. They are endomorphisms of OX, which are linear over p to the rth powers of functions, and then as I take r to infinity, I get every differential operator this way.
So this is compatible with this Brouwer, like if I didn't know the other circle of descriptions, I could maybe try to go directly to the, yeah. Oh, sorry,
Yes,
I was
so
gonna say
it is possible to do it directly. So if I have a Grothendieck TDO D, then D turns out to be a union of Azamaya algebras of rank p to the r times the dimension. And the assignment from weight 1 syntomic homology to this Tate module of the Brouwer group exactly sends D to the Brouwer classes of these azimuth algebras. And then when you do that, there's some ambiguity up to line bundles, and that's where Picard group tensor ZP comes in. So that's some sketch about how you might try to prove it. There's another approach to proving it, which uses more sophisticated machinery of stacks, and in particular the infinitesimal site, which is why the paper is called what it's called. But at the end of the day, it's really about some concrete statements of finite dimensional algebras. So let me give another kind of example. And I think this is the example that really made me want to study these algebras. If X is G mod B, then the Brouwer group of a flag variety is trivial. And so this syntomic cohomology is just the Picard group of G mod B tensor ZP. So what this means is I can consider an algebra differential operators on O of lambda. We're familiar with the line bundle O of lambda when lambda is an integer weight, but in fact, I can consider when lambda is a p-adic weight. And I think these algebras should have interesting representation theory, and people have not really looked at them before when lambda is not an integer.
But can you, do you have a localization theorem, like, for example, you take distribution algebra of SL2 that has a kind of Hrish-Chandra center, and the character of the center corresponding to the weight and Poisson. Is it related to that?
So there is a relationship to these hyper-enveloping algebras, but it's not as tight in characteristic zero and necessarily more complicated because these algebras are not in general affine. There's an example of
Well, they're not finitely generated.
they're not finitely generated, but I mean global sections may not be exact. So at least for SL5. So the story there is a little complicated. Let me not say more about it right now.
So the map from the distribution algebra to this is not surjective, or what happens?
Yes, the map from distributions to this is not surjective.
Even for SL2, or
Even for SL2. So since this is gone fishing, I know people like Lie algebroids, and so I want to say a little bit about Lie algebroids to finish. So for those familiar with the classification characteristic zero, if you take the operators of degree at most one, this is always a Lie algebroid. And the anchor map is exactly going to the associated graded, which is going to be the tangent sheaf. And then the kernel is the zeroth associated graded, which is functions. So there's this natural short exact sequence, and it turns out D less than or equal to 1 has the structure of a Lie algebroid. But in characteristic P, you can say even more. So if D is a Grothendieck TDO, and A is an operator of order at most 1, then in fact, A to the P, where I compute Pth power in the ring, is also an operator of order at most 1. This is something you can prove in one line using the definition in terms of commutators with functions.
Sorry, you wrote b greater than or equal to 1.
Oh no, thank you. Great. And so it turns out this D less than or equal to 1 in this case has the structure of a restricted Lie algebroid. Meaning, at least, that there's a P operation on this Lie algebra in the usual sense, and the P operation is exactly A goes to A to the P. Now, restricted Lie algebroids of this form, O going to A going to Tx to 0, restricted up to isomorphism, are also classified. So this is a theorem of myself and independently Dan Bragg. These are in bijection with H2 with coefficients in the group scheme of pth roots of unity in characteristic P. And it turns out that this classification is compatible with the main theorem I told you earlier, classifying Grothendieck TDOs. All right, that's what I wanted to say. Thank you for your attention.
Any questions? Yeah, yes.
If we want to see more about the relationship between the Pth power map and the Poisson structure, is there a good reference that we should look at?
So, you mean this Pth power map?
Yeah, so it has to have some compatibility with the action of O.
Well, so there's something funny about this Pth power map because the associated graded has divided powers. So if you try to raise, a cotangent coordinate to the P in associated graded, you get 0. So I don't know of other examples besides these Grothendieck TDOs where people have studied this kind of structure where I have divided powers. That's sort of exactly the whole problem. So in the sort of the other case where you don't have divided powers, then the work of Bezrikov and Kaleden explains some ways to impose compatibilities between Pth powers and Poisson.
Oh.
It's okay. So maybe it went too quickly for me. What was the relationship between your two theorems? I mean, there's like, I guess there's a traditional setting where there's maybe what is the enveloping
There
algebra?
is a map from H2 of X with CP of 1 and H2 of X from
It went too fast for me.
So, sorry. So I have TDOs,
Yeah.
and then I can map them to their degree less than or equal to 1 part. Then the main theorem was a bijection of this up to isomorphism with this H2 with coefficients in CP1. And there is a natural map from here to cohomology with coefficients in UP. So UP maps into GM. It's the kernel of multiplication by P on GM. And this short exact sequence induces this map. And then this square commutes, if you like.
And there's an enveloping algebra construction, is that related?
So I don't know how to define an enveloping algebra construction because this map is neither injective nor surjective in general. So these TDOs are really not determined by their degree 1 part.
Right.
I mean, you can take a kind of enveloping algebra, but this will be a different algebra which maps onto differential operators with kernel and co-kernel.
Okay, thanks. Yeah.
And is the question that I asked about developing of SL2 with divided powers, is it related issue? That you said that.
No, it is not a related issue. That's a separate issue from this.
Yes, I also want to ask, so there will always been my dream to try to define deformation spaces of, let's say, symplectic singularities that P with divided powers, which theoretic coordinates. And so it seems hard to do it in general, but at least is this procedure well compatible with quantum Hamiltonian reduction? So that suppose you have, so let's say some vector space, symplectic vector space, plus V dual, in which you have, so we define some divided power thing, and then you have a linear algebraic group acting on B, and you try to descend this whole story to downstairs. So
Yes, so in general, I don't know what to do. Somehow, the cotangent bundle comes with the structure of the zero section, and that is what makes the story work. If you just start with some symplectic vector space, then
no, let's say it's polarized. Let's say it's polarized.
yeah, so you take a polarization, and then what I can do is on this PD neighborhood of the polarization, which is really very small.
Yes.
And so if I try to do Hamiltonian reduction, I will get something, but that something will be, it'll have this PD fuzz, and I don't have some kind of general description of what this kind of space looks like. So, the theory of symplectic varieties with a PD polarization has not yet been written up. So that's the kind of issue for this.
So
Maybe at some point we should. At some point, I think we should, move the discussion to after the talk. Any more quick questions? Okay, let's thank the speaker again.
Because actually
So maybe
yes, things are divided.
there were too many ways of
That's
now I think I have a learned this.
I don't know, or